Good evening. This is Engineer David J. De Los Reyes, an electrical engineer by profession, an electronics troubleshooter also. We know hands-on troubleshooting other than this mathematics subject. Okay, let's proceed. My topic this evening will be a new topic on integral calculus. It is the so-called derivation of the circumference of a circle using parametric equations. The last time around, all my examples under length of arcs are actually circumference, perimeters, using Cartesian coordinate system. Tonight, I will be using parametric equations, and what will it pull under Cartesian maybe? Maybe after some manipulations, it will come out under Cartesian. Okay, let's proceed. My lesson for tonight, guys, is lesson 92 on my YouTube channel. Under the subject matter integral calculus, under the subtopic length of arcs. It is the computations of perimeters and circumferences for regular and irregular figures. But for tonight, I will discuss parametric equations in the so-called computation of circumference or perimeters. Okay, I will try to read the problem. Derive the circumference of the curve represented by the parametric equation. We are given a parametric equation, that is x equal to a function of theta and y equal to a function of theta. The parameter here is theta. So meaning we are given x as a function of theta and y as a g of theta. It's another function. So it falls under parametric. Okay? Where the parametric equations are actually x equal to r cosine of theta. R represents radius. Theta is angle theta. And the second equation is y equal to r sine of theta. The problem is asking for the circumference represented by the parametric equations x equal to r cosine of theta and y equal to r sine of theta. So actually, before we could figure out what will be the requirement, the figure, we should visualize our equation. X equal to r cosine of theta and y equal to r sine of theta. So it's a combination of x and theta. This is y and theta. Okay? Let's try to bring out the figure. Y-axis, x-axis. Why did I bring out the x and y-axis now? Because from here, later on, it will come out that the equations represented by x equal to r cosine of theta and y equal to r sine of theta is actually a circle with center at 0, 0. Later on, it will come out something like that. So if I will try to bring out the figure, okay, it seems we are given a right triangle, okay? This is the right angle. This is y, this is x, this is theta, and this is r. And from the given condition of the problem, x is actually r cosine of theta, and y equal to r sine of theta. Actually, the value y and x was derived from the right triangle, because if we take the cosine of this angle here, okay, cosine of this angle will be this side here over the hypotenuse, or x will be r cosine of theta, and the sine of theta, the sine of this angle, the sine of this angle here is this side here divided by this, or y will be simply r sine of theta. Okay. Right? So the equations represented by this is actually emanates from this right triangle here. As it turned out later, it comes out to be a circle, where the equation is actually x squared plus y squared equal to r squared. So it seems the problem is asking for the circumference of a circle. We will derive the general formula on how to take the circumference of a circle. Under Cartesian already, we know that the circumference for a circle is 2 pi r or pi d, pi times the diameter. Tonight, I will bring out this formula using parametric equations. Okay, let's proceed. From the equation x equal to r cosine of theta, taking the differential of both sides, dx will be r, the differential of cosine will be negative sine of theta, differential theta. Or dx will be negative r sine of theta, differential theta, equation number 1. You can mark your equations because later on these markings will be a reference when we go out to the so-called substitution. It's an easy matter to look at the numbering, and actually when upon the substitution, just look at this, you could proceed to the equation. That's the significance of this numbering here. From the second relation y equal to r sine of theta, taking the differential, dy will be r, the differential of sine will be plus cosine of theta, differential theta, or dy equal to r cosine of theta, differential theta. I will call this equation number 2. What comes out into my mind why I took the value dx and dy? Oh, it's just a simple thing, guys. Okay, I will try to erase this one. I bring out equations number 1 and number 2 because I was thinking that from the previous discussions, the length of arc in terms or under Cartesian is actually 1 plus dy over dx quantity square times dx. Okay? I was thinking of this. So I need a dy, I need a dx, and I need another dx over here. Oh, this is quantity square. So from equation number 1, I now got a dx. From equation number 2, I now got a dy. So if I need a dy over dx, if I need a dy over dx, okay, I could do it now. Why? Because I got now a dy here as a function of theta and dx as a function of theta. So if I will try to compute for the quotient of dy over dx, what we need here, okay, I will just divide equation number 2 by equation number 1. So what will come out? Dy is r cosine of theta differential theta equal to minus r sine of theta differential theta is this, equation number 1. Okay? So the markings got an importance because when I substitute here, I'll just go back to equation number 1 and number 2. So because if there are so many things over here, it's hard to look for it, right? So, but if I got the numbering, I will just go to the numbering, then I will try to substitute. Oh, just be systematic, guys. Therefore, dy over dx now will be equal to, this r cancels. Okay, we got the negative sign over here. So, and differential theta also cancels. Right? So what remains on the right hand side will be, dy dx now will be negative open quantity cosine of theta over sine of theta. Okay? But what we need in the differential length of r is actually the square of dy dx. So dy over dx quantity square equal to, there should be a negative 1 over here. Okay? So if we try to take the square of negative 1, this will not be plus, right? The square of cosine will be cosine square of theta, and the square of sine will be sine square of theta. Meaning, the value of dy over dx quantity square is cosine square of theta over sine square of theta. Okay? So if we now try to take this value here, go back to this equation. Okay, substituting now. Differential length of arc will be the square root of 1 dy dx quantity square is cosine square of theta plus sine square of theta times the value of dx. It is negative r sine of theta differential theta. The one under the radical sign, it's just an easy matter. Okay, 1 times sine square of theta, this is sine square of theta, plus cosine square of theta, all over sine square of theta. The operation inside is the division, so actually I could take the square root of the numerator and I will take the square root of the denominator separately. And since the denominator is a perfect square, okay, then later on, we could replace this one, okay, sine square of theta plus cosine square of theta is actually 1. So actually we could replace sine square of theta plus cosine square of theta inside by the value 1. So what comes out will be the square root of 1 all over sine of theta. The square root of sine square of theta will just be simply sine of theta. It's a perfect square. Times negative r sine of theta differential theta. The square root of 1 will either be plus or minus 1, right, over sine of theta, times negative r sine of theta differential theta. Sine of theta cancels, right? If we try to use the plus sign, a plus in a minus will be a minus. That's impossible, okay? But if we try to use the minus over here, a minus in a minus, this will now become plus, right? Or just simply r. R differential theta. See, so the resulting differential equation after the substitution of the square of dy dx quantity square, what comes out is a differential length of r. For this given problem is r differential theta. Integrating both sides. The integral of ds over 4 equal to, we bring out r. It is a constant, r. The integral from 0 to pi over 2 of differential theta. Why there is an over 4 over here? We now know that the resulting graph from the given parametric equation is a circle, and to take the circumference of a circle, just take the length from this point here to this, okay, then times 4. So this is over 4. If you don't want the over 4, okay, you multiply this by 4, then this is r. Okay, the limit will be from 0 to pi over 2 only, but we multiply it by 4 to complete the total circumference. So S now will be equal to 4r. The integral of differential theta is just theta. Easy money. The integral of differential theta is equal to theta. So this is theta with the limit from 0 to pi over 2. This is now 4r. Upper limit will be pi over 2 minus 0. But this is 0. Right? So this 2 here cancel with this. There remains 2 over here. So S now will be 2 pi r. This is 2 pi r. And instead of placing S for a circle, we term it circumference, so I will just place the capital letter C over here. 2 pi r units. Under lower mathematics, they are telling that diameter is equal to 2 pi. So circumference could be pi d. Okay? They are the same. Circumference for a circle as a function of diameter will be pi d, or as a function of the radius it will be 2 pi r units. So actually, the resulting parametric equation represents a circle with center at 0, 0, and the radius is r. Okay? It seems I just brought out the new derivation of the so-called circumference of a circle using parametric equations. Because sometimes there are problems in which the given equation is not a direct under the so-called Cartesian. It is represented as a function of a parametric equation. There is a third parameter, okay? It's not just only y equal to a function of x, or what I call this x as a function of y, but what comes out under parametric is x equal to a function of theta and y equal to a function of theta, and this is referred to as parametric equations. So just be very careful. Maybe you are expecting a Cartesian problem immediately, but on the first look, it is under parametric. So it's up to you to bring out or put it to the so-called Cartesian coordinate system for the solution to be more simplified. Okay, good evening, Los Angeles. That's the derivation of the circumference of a circle using parametric equations. Circumference for a circle is 2 pi r units as a function of radius, or circumference equal to pi d as a function of diameter. Good evening, Los Angeles.